Good day, everyone, and welcome. Today, we will explore how a CPU works, based entirely on the concept and explanations I've watched on the video provided by my professor, Sir Ryan. Um, so, by understanding its components, cycles, and historical evolution, we can see how simple operations scale into modern computing power. So, um, let's introduce the evolution of CPUs, focusing on the efficiency and its architecture. The first one that was created is the ENIAC, or what they call the Electronic Numerical Integrator and a Computer. This was massive, power-hungry, and programmed by rewiring hardware. It demonstrated electronic computation but wasn't practical for widespread use because, huge doesn't something that we can carry around. So that's why the Intel 4004 in 1971 was commercially introduced and you know make it available widespread. So it is a tiny single chip placed on an entire um it placed the entire CPU on a single chip, drastically reducing the size, the power usage, and of course the cost. So it's very much cost effective compared to the previous one. And then the Intel 8086, which is introduced in 1978, this was developed to expand this idea to a 16-bit architecture to a more complex instructions. When the IBM chose it for the first PC or program counter, its architecture times 86 became the industry standards. And yeah, it really defines the era of the computing. But in today's modern era, modern CPUs was of course based on these foundations. These are built on these foundations. They are far more powerful, but still they follow the same basic execution principle introduced by them. So it performs around billions of processes per second. So with this evolution in mind, let's examine now how CPUs are fundamentally organized. So the basics of CPU, the von Neumann architecture. So it defines how CPU operates. Instructions and data are shared in the same memory, but CPU executes instructions sequentially. Everything is represented in binary data. So uh, the following concept govern most modern computers, which dictates that the CPU's primary operational cycles involves around fetch, decode, and execute phase. Let's talk about the first phase, the fetch. So the control unit retrieves the next instructions from the memory, and guided by the program counter, this instruction is then placed into instruction register or the IR. Basically, it retrieves the instructions from the memory. And then, of course, we have the code base or the code cycle. The control unit interprets the fetch instructions, breaking it down into a constituents part, the operation code or the opcode, and any operands, data, or memory addresses. So basically, in simple terms, the code is the opcode and operands were identified. And yeah, lastly is the execute phase. So the decoded instructions is now being performed. This might involve the ALU. ALU or arithmetic logic unit, carrying out the calculation, moving data to or from registers or memories, or updating the program counter for the next meeting. So, um, to communicate with memory in this architecture, the CPU relies on what we call the special pathways, which is we call buses or the highway buses. So these are the addresses, the address, control, and data bus. So for the CPU to interact with memory, it uses these three critical communication pathways, which functions much like a delivery system. So the first one is the address bus. This selects the memory locations. So the next one is the data bus. Transfers the actual data. And then the last one is the control bus, which carries signals such as read, write, and interrupt. For example, the CPU sends an address. Signals read on the control bus. It receives data on the data bus. That's how it is. It's just it. It just says the pathway where the data was being transferred. So once the data arrives to the CPU, it needs extremely fast internal storage. So what are these? This is what we call the internal workspace, the registers. Within the CPU, registers serves as a tiny, ultra-fast storage location. They are the CPU's immediate workspace or immediate memory. It holds data that is actively being processed or critical information needed for the next step. The speed is paramount to the CPU's overall um, performance. So, um, there are three uh types or components that are inside the register. First one is the program counter. Program counters keep track of the memory addresses on the next instruction to be fetched and executed. So basically, it holds the address for the next instruction. Next one, the instruction register. So this temporarily stores the instructions that has just been fetched from the memory and is currently being decoded and executed. Simple terms, this stores the instruction. This stores the instruction. So basically, instruction register stores the current instruction. And lastly, um, the general purpose register. Basically, it used to hold temporary data during calculations and operation, acting as scratchpad for the ALU. So they are just the uh, temporary holder or memory for the data. So registers allows the CPU to operate far faster than if it relied on the RAM alone. So after loading the instructions, the CPU now decide what actions to perform. That's where the what we call the control unit and the ALU um happens or comes in. So these are the brain of the CPU. The CPU's intelligence largely resides in the two core components, the control unit and the arithmetic logic unit. Together, they all orchestrate all operations from interpreting commands to performing complex calculations. So these components, control unit and ALU, the control unit acts as what they call the traffic director of the CPU. It interprets the instructions fetched from memory and generate control signals to coordinate the operations of all other CPU components. It tells ALU what to do, when to access memory, and how to route data. So control units basically decodes instruction, controls data flow, and activates hardware pathways. And the next one is the ALU, or what they call the arithmetic logic unit. The ALU is the CPU's calculator. It is responsible for executing all the arithmetic um operations like addition, subtraction, multiplication, division, and of course other logical operation like and or not, the Boolean uh operations. So when the CU or the control unit decodes an instruction that requires computation, that's where the ALU comes in. It directs the ALU to perform the necessary computation. Yeah, LU performs arithmetic operation and executes logical comparison. So basically, that's the CPU's own calculator. So, um, for these components to work together into repeating for these components to be, for the whole CPU to improve efficiency, the CPUs overlap these steps. One I think that introduced it is the clock and the physical limit of thermal wall. So every operation within a CPU is synchronized by an internal clock, which emits pulses at a fixed frequency. So a higher clock speed generally means more operations per second. However, increasing clock speeds in definite phases and physical limitation. So basically the clock synchronizes operations. But of course there's a limit. Signal propagation delay and heat generation buildup. So this lead to more multi-core designs instead of faster clocks. The CPU, as the CPU runs faster, they generate more heat. Basically, uh, this challenge can be really you know can really slow down the process of the CPU. So solutions have made, and that's what we're going to tackle later on. So, um, so now we are here with addressing memory, and we have two different ways on how are we going to access the data in the memory, which is the direct and indirect. So understanding this method is a key on how the programs efficiently manage data structures. First one, we're going to discuss direct addressing. Indirect or implied addressing, the instructions specifies the exact memory, which addresses the where the data is located. This method is straightforward and fast, as the CPU doesn't need any additional steps to find the data. So, basically, direct addressing specifies a memory location explicitly. So there, it already straightforward. And of course, indirect addressing pointers is where it involves a two steps process. The instruction provide an address, but at that address, there isn't the data itself, but another address that points to the actual data. This method is crucial for implementing complex data structures like linked lists, arrays, and tables, offering flexibility and efficient memory usage. So basically, indirect addressing is where user points uh, a pointer. It uses a pointer storage is stored in a memory, allowing flexible data structures and efficient software design. Now, um, going to tackle the hardware interrupt, which are used for efficient task management. In early systems, CPU constantly had to call devices to check for input. If a key was pressed, this was inefficient. Hardware interrupts provides a much more effective mechanism for managing device interaction. So, um, the hardware interrupts allows devices to signal DCP. The process um, includes pauses its current task, save its current state, jump to special routine, store its previous state, and of course resume the original task. So this I can put this into analogy where um there's a key I got to give an example like when the keyboard input, there's a keyboard input and then suddenly you have a mouse hovering it. There's an interruption. So uh that's where hardware interrupts comes in. So it sends signals to the CPU. There's some actions ongoing, and then there's some actions, another actions that are going to happen. That's where it came in. So to pause safely, the CPU must save its states, right? That's done using its what they call the stack, a fundamental memory structure, or the what they call the method of LIFO, the last in and first out principle for temporary data storage. So this stack stores return addresses, registered values, and temporary data. The what they call this the last in and first out has push and pop operation. So when the CPU stores for example during the function call or interrupt, it stores the CPU states. It returns the addresses and temporary data to be pushed and pop as needed. So let's go on and have the architectural philosophy, the CXC and the RISC. The instructions set paradigm. The C the CISC is the complex instruction set computing. So this is single instruction perform multiple low-level operations. Programmer friend example is the Intel times 86 architecture commonly seen in desktop PCs and servers. While the RISC or the reduced instruction set computing, these are the simple instructions performs a single basic operation. The internal speed was much simpler, can be executed faster. The example is the ARM architecture, dominant in mobile devices and embedded system. So the CISC is complex instruction, fewer lines of code, more hardware complexity. While the RISC is simple instruction, faster execution, and yeah, more code. Modern modern CPUs today uses the hybrid approach, which appears CISC externally, and internally RISC like. So now we're going to talk about the another component in CPU which helps the ALU to perform its logic. I'm going to introduce the FPU or um the floating point unit. So early CPUs uses integer. So initial CPUs were primarily designed for just an integer arithmetic. So only one digit. Imagine that. But if you need this decimal, they can perform that. So now that's where floating point unit or FPU comes in. It is dedicated to emerge to handle decimal or the floating point calculations very efficient. So its integration into CPU were directly into the main CPU tab. So FPU significantly boosted performance for applications that requires precise mathematical computations, graphic rendering, and financial modeling. This integration marked a crucial step in making CPU more versatile and more um sorry and more powerful. So this floating point unit handles decimal floating point operations. So for example, if you calculate 1.5 plus 2.5, it will um generate a result of 4. If you calculate 4.5 by 2, it results to 6.5. So basically, it is used for decimals operation. So modern CPUs also supported multitasking. So we're going to talk about that in the next slide. Well, the evolution of multitasking. So the first one we call it the multi-programming. Multiple programs resided in memory, but only one runs at a time. CPU switches them uh in between when one waits for the input output. So it basically switches program when one waits for the input or the output. Another is the cooperative multitask. So the programs voluntarily yield control of the CPU. A misbehaving program could freeze the entire system. And the third one is the preemptive multitasking. This controls the CPU's slices, interrupting program to allocate resources, and this ensures system stability. So this allocates CPU time slices to ensure more stable operation. So another thing is for safe and efficient multitasking, which requires the memory management unit. So we have a key address translation, which maps logical addresses used by programs in RAM, and program detection, which enforces privilege levels, preventing one program from for, in, for interfering with another memory space, and of course the virtual memory, which enables the use of this space as an extension. So this MMU maps it maps the logical addresses to physical memory, enforcing the privileges and supports, of course, the virtual memory. So, for example, the user program cannot override the OS memory. The virtual memory allows application to use memory more than the physical instance. So, to improve speed without faster clock, CPUs use what we call the pipelining. This pipelining instruction execution overlap. It is the fundamental CPU optimization technique where multiple instructions are processed simultaneously. Imagine an assembly line, which while one instruction is executing, the next is decoding, another is being. So it's used for overlapping of instructions and executions. So for faster memory access, uh, CPU cake was introduced. CPU cake, bridging the speed to speed gap, bridging the speed gap. So CPU cake is a small ultra-fast memory located directly on or very near the CPU. It acts as a buffer. So basically, it is the temporary storage where it is accessed by the CPU to be accessed again soon. I mean, it is stored for the process to be accessed again. So we have two types, the temporal locality and the spatial locality. Temporal is being accessed, uh, is being stored and then accessed and be accessed again soon, and then spatial is being accessed now, and then nearby memory uh locations are likely to be accessed to another memory. We also have what we call the cake hit. The cache hit means the data is found in the cache and resulting in a fast access. And the cache miss means the data must be fetched from the slower main route. So um basically cache stores frequently used data closest to the speed, so it can be accessed more easily. So understanding CPU evolution helps contextualize these improvements and of course the CPU architecture. Yes. Summary. Yeah, we already tackled that already. So the Intel 404 is the first commercial available microprocessor, a 4-bit CPU. Next one is the Intel 8086, and then the 1985, which introduced the 32-bit times 86 processor. And then later on, we have the 1980s Apple's 86K Max. And now the modern era, we continued times 86 dominance with with the multi-core, 64-bit, and advanced power management in ARM. And then, of course, in summary, the journey through the CPU architecture reveals a continuous quest for speed, efficiency, and functionality. From simple instruction sets to complex pipeline design, each innovation has profoundly impacted computing. So, a CPU orchestrated computations throughout these components. The ALU, which performs the arithmetic logic. The control unit directs the traffic. The registers for fast storage. The buses that move the data instructions or deliver the data instructions to the components. And then the cache, which uses for quick memory access. And of course the MMU for a secure memory mapping. So this these things, the key components, then the modern features that was integrated were a multitasking and solutions for the problems like overheating was used. And yeah, this is the CPU's main cores, components, and system architecture. Well, this knowledge should prepare us how to understand modern CPU innovations and performance optimization. CPUs are highly efficient, precise, and complex machines. Through pipelining, peaking, and multi-core design FPUs, modern CPUs execute billions of instructions per second. Understanding their structures and operations, it provides insights into how computers perform complex tasks efficiently. That's it, and thank you. I hope you have learned something from this video.